Welcome back. This is the notes for the mechanical power transmission. This is video 2. Today we're going to begin by talking about gears. And looking at this picture here, we want to know which gears will mesh. Which gears will fit together so that they can turn each other. Alright, so looking at that, I think we can obviously see that it's going to be this gear meshing with this gear. Now there are two requirements for gears to mesh. The first requirement is that they need to have the same size teeth. The second requirement means that they have to have the same spacing between the teeth. And I think you can see that that requirement's been met with these two gears. They have the same size teeth, height-wise, and there's the same spacing between them. Now, there is a relationship between the number of teeth on each of the same type of gears. And that means that these will be proportional to the diameter of the gear. We call this diameter pitch. The VEX system uses a 24 diameter pitch gear. So here's what that means. Earlier, I measured out the diameter of each one of the gears. Now, what we have in class is we have 4 different gears. We have a 12-tooth gear, a 36-tooth, a 60-tooth, and an 84-tooth. And I measured out the diameters. For the 12-tooth, it's 1/2 inch. We use that symbol, like the quote symbol for inch. For the 36-tooth, it's 1.5 inches. For the 60-tooth, it's 2.5 inches. And for the 84-tooth, it is 3.5 inches. So 24 diameter pitch tooth. Well, here's what's kind of cool. If you take that 24 and multiplied it by 1/2 inch, it gives you 12. If you take the 24 and multiply it by 1.5 inch, it gives you 36. I think you're starting to see the pattern here. So what this is it's a way of standardizing the gears. So let's say, for an example, I need a gear with 96 teeth. I would need to, sorry about that. I would need to know what the diameter of that gear would be if I wanted to put it into a gearbox, just to make sure that everything fits. Okay, well, if I were to take 96 teeth and divide it by 24, I get 4. So I find that a 96 tooth gear in the VEX system would have a 4-inch diameter. All right, I now want to talk with you about gear ratios. Gears themselves do more than just transfer power. They also provide us the opportunity to adjust something called the mechanical advantage of a mechanism. So to begin with, let's think of a bicycle rider. The rider themselves is the motor, and they have limited amount of power. But remember, as you increase the load on a motor, the torque increases, but the rotational speed decreases. So as you might imagine, when you're on your bicycle and you start to climb a hill, there's more torque, so you're pumping out more torque with your legs, but you also slow down. So for a bicyclist then, what we want to do is we want to use a machine to make sure that we are harnessing as much of the power of the person as we can. So if we're going downhill, the load is low. So what we would want to do is we would want to use a gear ratio that would increase the speed and have a low output torque, because we don't need as much output torque. We want to go fast. If we're going up a hill, the load is high. So that means we would need to use a gear ratio that would increase torque, but it would sacrifice speed. And we can do that. You know, for the bike, the mechanical advantage changes. As you select different gears, you're choosing different mechanical advantages. So the speed of the motion also changes. A little bit of review here. Remember that power is the rate at which work is done. You know, power is work over time. So if the amount of work increases, the speed at which it gets done decreases. That's assuming we have constant power. Now, machines themselves. First off, you need to understand that a machine does not increase how much work you can do. So when we have a machine, the input work, the amount of work we put into a machine, equals the amount of work we can get out of the machine. We can't change that. So machines do not reduce the amount of work we can. It just doesn't reduce the amount of work. We have to do the same amount. Okay, well, remember that the definition of work is force times distance times cosine of the angle between them. The force and distance have to be parallel. So we'll go ahead and assume theta equals 0. That way it makes it a little bit easier. So when we take a look at, for a machine, we see that the amount of force we put into a machine times the distance we have to travel equals the amount of force that comes out of the machine times the distance that the machine moves. So the distance in is how far we move the machine. The distance out is how far the machine moves. The force in is how much force we put into the machine, and the force out is how much force we get out of the machine. And just doing a little bit of extra math here, we see that we have this relationship. The distance that we put into the machine divided by the distance we get out equals the force we get out of the machine divided by the force we put into it. And this leads us to mechanical advantage. Mechanical advantage makes it easier to do work. I'm going to abbreviate mechanical advantage MA from now on. And the way that mechanical advantage makes it easier to do work is that it multiplies the output force. So for the math for mechanical advantage, the mechanical advantage would equal the output force divided by the input force. But remember this relationship here, that means that it also equals the input distance divided by the output distance. So looking at this this picture we have here, we have a lever, and if I were to apply a force right here, if I were to apply a downward force, that's my input force, I would get an output force. This 8 meters would equal my input distance, and this 2 meters would equal my output distance. So if I were to do a little bit of math here, I would see that I would have 8 meters divided by 2 meters, which obviously equals 4. So my mechanical advantage is 4. So another way of thinking about this, if my input force were 10 newtons, my output force would be 40 newtons. However, in order to do that, I have to travel a large distance. That's where the second part comes in right here. Notice that it's a little backed up. Let's say this is in and this is out. Notice that in order to do that, I would have to travel a distance of 4 meters for every distance of 1 meter I would get out of the machine. Now, what else is kind of interesting about these distances is that they move at the same time. So let's say it takes 1 second for the input to move 1 meter. If I were to apply it to the problem that we just did, to move the, let's change that to 4. It takes 1 second to move those 4 meters. At the same time, that output moved 1 meter in 1 second. So what we can say is that the output would be moving slower than the input by the ratio of the lever lengths. So going back up to this, again, if this is my input and this is my output, if I'm traveling at 4 meters per second, if that's my input, my output would only travel at 1 meter per second. This whole process is reversible. If I do this all backwards, if this side now becomes my input and this side becomes my output, the math is identical, but the numbers will be reversed. My mechanical advantage will be 0.25 instead of 4, which means that if I put in 10 newtons of force, I would get 10 divided by 4. I can't do math this early, but it would be 10 fourths. It'd be less output force. At the same time, if I moved at 1 meter per second for the input, the output would move at 4 meters per second. It would be faster on the output. So we see that there's this relationship. There's this give and take between speed and force. We also need to apply torque to this whole situation. So for example, let's say that this right here is my output this time. This right here is my input, and I'm applying 4 newtons of input force. My input distance is 2 meters. My output distance is 8 meters. And there's a certain amount of torque because as I press down on this lever, I'm applying a torque to that pivot. Now remember that torque is force times lever arm distance times sine of theta. And we can see that theta in this case will equal 90 degrees. Sine of 90 is 1. So we can just use a simplified version. Torque is force times lever arm distance. So when we apply our mathematics to this, the input torque would equal the amount of force we put into it times the input lever arm distance. So that's going to equal 4 newtons times 2 meters. So that's going to be 8 Newton meters. The mechanical advantage of this system, which is equal to the input distance divided by the output distance, would equal 2 meters over 4 meters. Oh, sorry, 2 meters over 8 meters, which equals 0.25. Now, just like force, torque is the rotational equivalent of force. The input torque times the mechanical advantage would equal the output torque. So if I had 8 Newton meters worth of input torque times 0.25, I would get 2 Newton meters of output torque. Likewise with force, the input force times mechanical advantage equals the output force. So if I had 4 newtons times 0.25 equals 1 newton of output force. Now, gears themselves, we can think of a gear like a lever, where the radius of a gear is the lever arm distance, and the fulcrum is the point right between the gears. A spur gear, then, we can think of it as a series of levers. The larger the diameter of the gear, the longer the lever. So we can apply all that same math that we just did. So looking at this setup here, let's say that this side right here is the inside, and this is the out. So we got our input and our output. If I look at the input torque, everything's at right angles, so we don't have to worry about the sine function. We get that. We take a look at the output torque. The key to this, however, is that the forces here this time, because these gears are connected right here, that input force is the same as the output force. And think about it. The amount of force that this gear pushes down will equal the amount of force that this gear gets pushed. So those are the same. So what that means then is that we can get rid of the output and the input, and we just get force here. And that means that I can set both of these equal to a force. I can say that this force equals the input torque divided by input radius, or lever arm distance, and this force equals the output torque divided by the output radius, and I can now set those equal to each other. And I can do a little bit of algebra here, and I see that the input torque times the ratio of output radius to input radius equals the output torque. And guess what? This is our mechanical advantage. So in conclusion then, when we have small gears driving large gears, that means we get more torque, but we sacrifice speed. When we have a large gear driving a small gear, we get less torque, but we gain speed. Talk to you later.